All right, Calculus 12, here we go again. Another beautiful May day. And we're going to do some more trig here. And we're going to actually start trigonometry. So this is a good day. So we're going to start trigonometry with calculus. Here's the good news. The good news, and the bad news, actually. Let's do the bad news first. The bad news is everything you've learned in calculus to this point, from limits, derivatives, all the derivative rules, all implicit differentiation, max-min problems, related rates, curve sketching, concavity, everything you've learned is now just going to be redone through the lens of trigonometry. Okay, so that's the bad news, because it's going to redo it all again. So, but that's also the good news, because if you know all of that information, it's basically everything you've done, just putting a layer of trig on top of it. So here we go. First of all, chapter 6 in our textbook is all pre-calculus 12 review. So if you need some trig review of trig identities, trig equations, evaluating trig expressions, trig graphing, it's all in chapter 6. So we're not going to do that chapter at all. That's not because of the situation we're in. I never do chapter 6 because you've already done it in pre-calc 12. That's the expectation that you should have going in. So trig limits start on chapter 7. 7.1 is all about trig limits. So here we're going to roll with some trig limits. Just a review of, first of all, here's a whole whack of limits, but notice the only difference is now trig can come into the play with your functions. Remember limits. You could do a number of ways, and no real changes you'll see today, except for a few new things that are added to the plate. You can do limits either numerically, or you can do them graphically. So if someone asked you what the limit as x approaches 0 of sine of x would be, you could do the little plug-in rule. If you plug 0 into here, sine of 0 is 0. Or you could graph sine. There's the sine graph, which you have to remember from pre-calc 12. As you approach 0 from both left and right, the y value approaches 0. So I'm just showing you that there's no difference. You just have to have a little bit of trig knowledge. Sine of x as x approaches pi over 2. So you could plug pi over 2 in here and just know from your trig table sine of 90 degrees or pi over 2 is 1. Or you could go to your trig graph and say, as I approach pi over 2 from both left and right, I am a value of 1. Cosine of 0. The graph, as you approach 0, is 1, or cos of 0 is 1. Cos of pi over 2 is 0 from the graph or the evaluation of it. Tangent, make sure you know your tan graph with all the asymptotes, good times. Tan of 0, well, there's either 0 or just looking at the graph at 0. Tan of pi over 2 from the right, so as I approach this from the right side, tan of pi over 2, according to the graph, is negative infinity. So there's me approaching pi over 2 from the right. Oh, I'm way down here. That's where I find the graph handy. Without a graph, that one would be a troublesome one for me. And sine of pi over 2 from the left is going to be infinity. And just to throw it in there, I guess if they had asked you tan of pi over 2 from left and right, because they're different, this would be a does not exist situation. Okay, so that's just a basic trick. You can always do any limits, like I said, by evaluating or graph. Obviously what's going to happen is evaluation is going to become more difficult, graphs become more difficult, and we have to have other algebraic strategies. One limit that is going to be really, really, really important for you is sine of x over x as x approaches 0. And we'll see why that is an issue later on and why we have to focus on this. But just trust me on that. If I plug 0 in right now as my quick evaluation without a graph, because I don't know what sine x over x looks like without a graphing calculator or Desmos, this gives me 0 over 0, and there's our little buddy that comes out with limits. That is, remember, indeterminate. So this could have a value. We just don't know what it is. At the moment, if I don't know this knowledge, remember my ways out. I could go to my calculator, and this is nothing wrong with this, and I could go and graph it with Desmos or with a graphing calculator. And when I graph this, here's my funky little graph. It looks kind of like a modified sine graph where the amplitude is actually just diminishing. Looks like a weird octopus. And as you approach 0, if I trace on this thing, as I trace close to 0, I see the value is really close to 1. There's actually a hole right there. So this is actually 1. The other way of doing it would have been able to do it numerically. I could plug a number in. I could just go sine of a number close to 0, 0.001 divided by 0.0001, and I could see it's around 1-ish. I might prove to myself that as I approach it from the negative side, it's not just a fluke. And I also get 1. So the answer for this right now, without really proving it, is the limit of sine x over x as x approaches 0 is 1. And I'm going to write that really big, because that's one thing that is huge with trig limits. You'll see this comes out quite often. That is just a fact you need to know. Tattoo it to your heart, all right? Or your mind, or tattoo it to your skin if you want. And that's going to be one thing that's important. So what I'm going to, if you want the proof of this, and again, this is the first time I've done this. I'd never thought I'd get to this with the YouTube stages. Click up here in the top corner. There should be a little link. I'll have a proof for you, but the proof is not mandatory for Calculus 12. If you go to university, you might have a prof that also thinks the proof is not mandatory. You might have a prof, though, that loves proofs, and proofs might be part of the course and part of the tests and exams. So it's nice to kind of see this, but for Pre-Calc 12, that is optional. All right, so let's get on to limits, knowing and understanding that this is true. So here's the process. So again, just don't get overwhelmed by what's on here. We're going to do a whack of examples because I think that's the only way to get through this. So for any kind of trig limits, you're going to use all the same strategies you did for limits. So first strategy is plug in, any kind of algebra factoring, expanding, rationalizing, lowest common denominators, all that stuff you still keep in the back of your pocket to use. But also now with trig, you have identities. So if you can find an old trig identity sheet, I might link that to, I think I will. I'll put that on as an extra PDF in case your trig identity sheet has been lost from Pre-Calc 12. You need your trig identity sheet possibly, and then you need this fact. The limit as x approaches 0 of sine x over x is 1. That's going to come into play big time. All right, so here we go. Example number 1. So I see a limit. I don't freak out. My first thought is, okay, I'm gonna plug in the value. That's what I always do. So what is sine squared of pi over 6? Can I evaluate that? And sure enough, I can. I don't have any division by 0. So remember what this means. This just means sine of pi over 6 all squared. Sine of pi over 6, I'd have to go back to my trig table. It's been a long time. Sine of 30, sine of 30 is a half. So I should know that fact. If I don't, well, there's my roadblock, not my calculus. It's my Pre-Calc 12. And then you end up with a quarter. Now remember, if I really didn't know this, I could go to my calculator and type that in, assuming I have a calculator, or I could graph sine squared and do it that way. That's up to me. This was just, I'm done. There's my evaluation. It's over. Okay. Next guy. So that didn't have any strategies except for plug it in. Next one is sine x over 7x. So I would try plugging it in. So sine of 0 over 7 times 0. Sine of 0 is 0. 7 times 0 is 0. So I've got that, our little friend, indeterminate state. So now I think about all the strategies. Does this scream factoring and expanding and LCDs? No. Does it scream any trig identities? Not really, because there's no double angles and I don't see any sine squareds. So my only hope is this guy. But notice how it's very close, but the trouble is there's a 7 here. So I need to algebraically extract this. And sometimes that's really easy. So in this case, here's my one little step. Would you agree that sine x over 7 times x is the same thing as 1/7 times sine x over x? And it definitely is mathematically true. Those are the same. I know this fact now. This is a fact I can carry around as a piece of knowledge. I know as x approaches 0, and it's really important, it must be approaching 0. As x approaches 0, sine x over x, I know for a fact that is 1. So you end up with 1/7 times 1, so this gives me 1/7. And you can check it out. You can go and graph that function and see what happens as you approach 0. You'll see it's 1/7. Next guy. Again, looks very similar to this, but again, let's not jump in too quick. Let's just try plugging in 0. So plug in 0, and yeah, and sure enough, I get sine of 0 over 0, which is 0 over 0. Here, though, very different than this one. Here, that 7 was not an angle inside the sine, so I could factor it out, so to speak. This 3 cannot come outside here without using a trig identity or some other kind of manipulation. So what we're going to do, and this one's kind of a special one, but it's a good one. I want to make this similar. So what I'm going to do is, if you look here, these are the same. This angle inside the sine is x, and it's being divided by that same angle. These have to be the same. Right now, I would love there to be a 3 here. Love. So what I'm going to do, I'm going to put a 3 there. I'll do it in a different color. I'm going to put a 3 there. But remember, I can't just put a 3 there and say those are equal. If I multiply the bottom by a 3, I have to multiply the top by a 3. So you might look at that and say, well, there's no difference between those two, and there isn't, because that 3 is dividing out. But what it has done, it has made this sine of 3x divided by 3x, or you can think of it as think of this as theta divided by theta, which is what this would be here. Sine of that angle divided by the same angle is 1. These have to be the same, and they are. So this whole thing approaches 1. And you end up with 3 times 1, which is 3. Now you might look at that and go, well, next time I did that, if that was an 8 there, I'd get an 8 out. And yeah, you can get crafty with it, but make sure you know the reason why you're using this kind of limit proof. Next one. Plug in. Plug a 0 in. I get sine of 0 over sine of 0. Crap, that's 0 over 0. What can I do? And I look at that and go, man, first of all, I am not allowed by any way, shape, or form to divide out the sines. Okay? It's like that really sad joke. You've probably seen me talk about it before, where the person has sine x over n, and they cancel out the n's, and they say it equals 6. S-I-X. That's funny and sad at the same time. So, can't do any canceling. Nothing. All I can do is think about identities, other algebra, but I don't see any identities here that scream out anything, because I don't want to work with the sine of 7x or sine of 4x. So what I'm going to do is I'm going to try to pull this guy out. This guy is kind of your key most of the time. First of all, there's a mistake on here. This should be variable x. Otherwise, it would make no sense. So variable x approaches 0. So here's what I'm going to do. Just bear with me. And I only know to do this because someone else showed me. What I'm going to do, I'm going to do it in stages. I would love this sine 4x to have a 4x below it, so I could invoke this. But if I put a 4x there, I have to put a 4x there to keep it algebraically balanced. But now what I've done, I've created this. And sine of 4x over 4x as x goes to 0, that goes to 1. And I'm left with this, sine of 7x over 4x. Now it's too bad that wasn't a 7x, because then I'd be laughing. But what I'm going to do, because I can do whatever I want as long as the algebra works, I'm going to keep this x here, but I'm going to put a 7 there, which means I have to multiply by 7 there, and don't forget there's also a 4 here. So that 4x stayed. I threw a 7 on the bottom as a timesing, and I threw a 7 on the top to keep it equivalent. This then goes sine of 7x over 7x as x goes to 0. That goes to 1, and you're left with 7 over 4. Now, to the poor novice person that looks at this, they might look at that and go, well, that's easy. I can just cancel out the sines and cancel out the x's. That is not the right reason. It's just total flukage, okay? So do not do that. Make sure you can do it with the real reasoning behind it, okay? Next example. Like I said, we're just going to go through a whack of these. limit as x approaches 0 of cos x minus 1 over x as x approaches 0 here. Okay, so again, plug in 0. Cos of 0 is 1, so you get 1 minus 1 over 0, and 0 over 0 again. Alright, so unfortunately that didn't work. Just shows me that this has a different approach, so it's indeterminate. I look at this, and man, I don't see any factoring. I don't see any LCD work's already done. I don't even see a sine x over x in here. I mean, I have a cos x over x partially, but that's not the same. So my only hope is I'm gonna have to play, and the only thing I can play with here is a some kind of trig identity technique or some kind of algebra. And what I'm going to do, and again, this is only just through sheer practice. It's like when a patient comes into a doctor, some doctors that are really experienced, that have done a lot, they know right away, boom, I know what you got. I'm going to multiply by the conjugate. That's my only algebraic hope here. I'm going to multiply top and bottom by cos x plus 1. And then cross my fingers and hope for the best. So my numerator becomes cos squared. There's a plus cos and a minus cos that cancels out with the conjugate, minus 1, all over x times cos x plus 1. Now the reason I did that was a hope of something happening. Remember from pre-calc 12 that you know that sine squared plus cos squared equals 1 on your trig identity sheet. Hence, cos squared minus 1, if I manipulate this, cos squared minus 1, if I move the 1 over to here and move the sign, equals negative sine x. So I can replace this mess, which it is a mess, it's not clean. I can replace that with sine squared. Negative sine squared x over x bracket cos x plus 1. Looks worse, but I see a sine x over x in here. The squared kind of throws me off a bit, so what I'll do, I'll just write the sine squared as 2 sines. That's all it is, sine times sine. And here's my moment of possible happiness. Sine x over x, because that's all multiplying now, as x approaches 0, this goes to 1. And I'm left with, and I'm so hopeful, but I don't know yet, I'm left with this mess. Please, 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 when I plug in 0, give me an answer. Negative sine 0 is 0. Cos of 0, though, is 1. Ooh, 1 plus 1. I like that. 0 divided by 2. That's a nice number. That's 0. So there's my answer. The limit as x approaches 0 of cos x minus 1 over x is 0. And that's actually one, you can memorize that fact if you want. Some people actually use this as another, like the sine x over x as x approaches 0 is 1. They also memorize this cos x minus 1 over x is 0 as another fact if you wish. But there's the proof of the fact. Tangent of x over 7x as x approaches 0. Plug it in. You never know. Ah, crap. Tan 0 over 0, 0 over 0. More work to be done. So, what do you see? I know what I would try. I would use a trig identity on tan because I want sines and coses. I can treat this as sine x over cos x over 7x. Remember, that's over an imaginary 1. So if I flip and multiply that, this is where your trig identity experience comes in. So I get sine x over cos x, and that flips and multiplies, and I got a 7x on the bottom. Now when I look at that, it screams to me, if I remanipulate it, I'm going to write it like this. 7 times x times cos x is the same thing as x times 7 times cos x. And look at that. Sine x over x, boom, as x goes to 0 is 1. And you're left with the limit as x approaches 0 of 1 over 7 times cos x. Plug in 0, cross my or hold my breath. Cos of 0 is 1. Boom, I get 1/7. Done. Alrighty. Next example. And the last, I'll do this one quick. You can always fast forward. That's the beauty of the internet. If you don't like all my examples, we're up to 20 minutes. I don't want to go over that, but I am. It's probably going to be about 25 minutes. All right, when I look at that, I would plug in 0 first. I get 0 times cotan of 0. Cotan of 0. That one would bug me. I'd have a hard time to think about that one for a minute. So what do I have? Well, I could write it as 1 times 1 over tan of 0, which would end up with 0 over 0. So I'm in the same boat. And cotan just screams, please rewrite me as cos over sine. Alright, now I'm looking for sine x over x or sine theta over theta. Now I have sine theta over theta, but backwards. Does that go to 1? My hunch says yes, but I can't go on hunches. So what I'm going to do to make this work, beyond a shadow of a doubt, I'm going to put a theta here because I want it. I want that to be sine theta over theta, but I'm going to multiply by theta there. I've created this going to 1. This, by coincidence, canceled. And what am I left with? I'm left with the limit of theta approaches 0 of cosine theta. When I plug 0 into that, cos of theta equals, or cos of 0, sorry, equals 1. There's my answer. Okay, we got 2 little examples here. Well, not little, but they're fun. So again, I would pause it and try it. I've done these before, so I know exactly what to do. Again, if I plug 0 into here, I get 0 over 0. Because if not, I'd be done. I would personally, that screams an identity. Double angle, because I can't factor out a sine, because that's double angle, that's not. So this screams double angle identity. Sine 2x is 2 sine x cos x over 5x cos x. Now I've created a situation where I can factor out a 2 sine, so I'm going to do that. I don't know where this is going yet, but it gives me hope. Factoring always gives me hope. And I end up with 5 times x times cos x. Everything's factored. Do you see anything in there that possibly gives me a sine x over x? I do. Boom. That little turkey goes to 1. I'm hoping that cleared up my problem. If it didn't, I'll cry the blues a little bit, then get back to it. But let me just see what I got. Alright, I got this. I'm going to be hopeful, because that had some hope there. I'm going to plug in 0 and hope. If I plug 0 into this, does it give me hope? So first of all, cos of 0 is 1, so I get 2 times 1 minus 1, which is 0. That's not very hopeful in the numerator, but the denominator is 5 times 1. So you end up with 0 over 5, which is perfectly fine. That is 0. So this whole mess approaches 0. If I had graphed that on Desmos, it would have been a mess, but as I approach 0 for the x, the y value would have approached 0. That's what I know about that graph. Okay, last one. This one, I would plug in pi right away. Now, because it's the last example, I might get lucky and be really simple, but remember, sine of pi is 0. Pi minus pi is 0, so no, I didn't get lucky. Shoot. My only dilemma here is, remember the rule is sine x over x as x goes to 0 is 1. This is not approaching 0. This is approaching... It has to approach 0 for this rule to work. This is approaching pi. So even if I put an x on the bottom here and an x on the top, that would not, I wouldn't invoke this rule because that's not going to 0. So what I'm going to do is here's a sneaky move which we haven't talked about much. It's called like a dummy variable replacement. I'm going to let u or m or whatever letter I want, but usually we use u. I'm going to let u equal pi minus x. Okay, if I do that, if I make that statement, so there's my claim. I'm going to let u equal pi minus x. then would you also agree if I manipulate this, x would, if I solve this for x, would equal pi minus u? Just bear with me for a minute on that. Okay, so and also, as x is approaching pi, which is what's happening here, u would have to approach, if I plug pi in for this x, would have to approach pi minus pi, which is 0. So here's what I end up with. I take this original question and just watch what this morphs into. Now it becomes a limit as u approaches 0, because I've made the replacement with u. Sine of x gets replaced with pi minus u, and the denominator pi minus x gets replaced with u. Now you might look at that and go, man, you've made it worse. In some ways I have, but at least this is going to 0 now. This numerator screams using using the sum and difference identities. So this would then give me, using the sum and difference identity, sine of pi times cos of u minus cos of pi times sine of u over u. Sine of pi is 0, so this becomes a 0. Cos of pi is -1. So I end up with negative -1 times sine of u over u. So I get sine of u over u as u approaches 0. That's 1. Now that's an awkward one. There are other ways of doing it, but that's that particular question completed. So we're going to end there. That's the start of trig. I did a lot of examples, more than I maybe had to, but that's what you need to do too, is just do example after example after example, making sure it's for good reasons. Over and out. Have a good day. Talk to you soon.